Number 4, in number 3, there is no surge impedance, but in number 4, there is surge impedance. That's the only difference. Number 5, okay, number 5, this is N tower. So it's similar with number 2, except there's only one ZE, because the tower is the N tower. So the earth wire is on one side only, no earth wire on this side. And the earth and the strike is at the top of the tower there. So you can calculate this. Okay. Let's give a question. Any question? Anyone has any question? I have talked before, the voltage shape will follow the current shape. Okay. You need to understand one important thing. The shape of a current or voltage, for that matter, has 2 important parameters. The first one is, so this is, let's say, current or voltage, if you like. This is time. Starting from 0, the current will rise or the voltage will rise. I just use a straight line there. And then you reach a peak and then it will decay. But because it takes so long, almost straight line there. So the time, this is T peak. It's very important. The time to peak is very important. If the time to peak is 1 microsecond for the current, so the voltage also have 1 microsecond time to peak. It doesn't matter what is the peak, but the time to peak is the same. Why I said it doesn't matter the magnitude? Because for the current, the magnitude will be current in amps, but voltage will be in volts. But if you have attenuation, for example, due to propagation, okay, you cannot see that line. If you have attenuation, then the voltage or the current will be reduced, but the time to peak is still the same. If it get reflected, it's the same thing. It can be a fraction of the original voltage. Or if it got transmitted, it can go a bigger voltage. But one thing that is maintained is time to peak. It can even go negative. But still, one thing that is maintained is time to peak, regardless of the magnitude. The time to peak always the same. So let me stress this. Time to peak remain the same. Who doesn't understand this word? Okay. Next, we move to the, let's say we have a surge striking mid-span, like this. So you have a tower, and there's earth wire at the top. There's another tower at the other end. Let's say it strike here. So one surge will go to the left, the other one to the right. I mean, should be at the bottom there. So surge will travel to the right, to the left. So there's a voltage here, voltage to the left, and voltage to the right. The voltage can be said as incident voltage. This incident voltage will arise at the top here, also the other one. So when it arrives at the top of the voltage here, or of the tower there, this voltage, when it arrives, then we have a situation of this. Remember, we have surge impedance of the line, the surge impedance of the line after the discontinuity point. Okay, this is discontinuity point. This is also important. Discontinuity point. We have 3 things. There is the transmission line that is traveling Z earth. There is another transmission line connected after this discontinuity line, which is also Z earth. And there is also another transmission line, if you like, the tower itself. So there are 3 things connected at that discontinuity point. I repeat again, if you have a transmission line striking, if you have a earth line struck by lightning, so the model is like this. You have Z Earth surge traveling from the middle there to the left. And when it arrives there, it can continue moving on to the left. At the same time, it also see another surge impedance, which is Z tower. So the current is split into two, if you like. To continue on and to go inside the tower. So you have a discontinuity point like this. So in this case, how you want to calculate alpha, because some of the surge that arrive, we call it incident wave, will be reflected. So that's alpha, and transmitted. So it has transmitted into ZE as well as Z tower. So how to calculate alpha and beta in this case? So what you do, you have to make the equivalent circuit for this like this. So this is Z Earth, and the surge travel from the right there. When it reach the discontinuity point, it will see two surge impedance, ZE and Z tower, right? But you can combine this into Z equivalent. And the equivalent of the two is actually Z Earth parallel with Z tower. Okay? So at that discontinuity point, you can now calculate alpha and beta. So the voltage coming from the right here, we call it V incident, will be reflected by alpha times beta. So there's a voltage coming this way, alpha V incident, and the voltage going this way, which is beta V incident. Okay? At the discontinuity point, you still have the same voltage. That means beta incident is equal to V incident plus alpha V incident. Okay. So if you look at the slide, Z2 now is actually Z Earth in parallel with Z tower. So Z2 is the one on the left here. Okay. And Z1 is actually this one. So this is Z1. This is Z2. Therefore, you can calculate alpha and beta. Already described the incident wave is given by beta 1, beta V incident. Now, the two wave that is transmitted are the one that goes towards the left into the transmission line, moving on, and the other one into the tower that goes down the tower. Now, the one that goes down the tower, and the tower having a surge impedance of Z tower, will take some time to reach the bottom. And the time is given by this formula, where H is the height of the tower, and Cs is the propagation speed. So the surge, if you like, will travel at the speed of Cs. And the time taken from here to here to arrive will be, and therefore T is equal to H divided by Cs. The height or the length travel divided by the speed. Okay, next slide. Okay, before that, let me remind you, we have that the surge arrive here. Some of it will travel this way. Some of it will be transmitted into the tower. Okay, so the one that transmitted into the tower, but some of it also we got reflected. The one that got transmitted into the tower, we reach the bottom of the tower. When it reached the bottom of the tower, this voltage is actually beta V incident, or V source, if you like. V source is the source coming, or incident voltage. And the voltage that goes into the tower is beta Vs. This beta Vs will go down the tower, And when it reaches the bottom of the tower, it will be reflected again, because at the bottom of the tower, we have our grounding or tower footing resistance modeled by this R. So when the surge propagate down, beta Vs, from the transmitted lightning, from here, it got transmitted inside. So this is Vs going in here. When it reaches this point, you have another discontinuity point. So you can model this like another transmission line system with a discontinuity, Z tower and R, if you like. And at this point, you have what we call another discontinuity. And therefore, the surge that goes in, which is beta 1 Vs, will be reflected, another alpha, so we call it alpha 2, and will be transmitted, we call it beta 2. Okay? So at the bottom of the tower, there is another discontinuity based on the surge that goes into the tower, which is beta 1 Vs. This one, beta 1 because the first beta. It will be get reflected by alpha 2 at the bottom of the tower, and some of it will be injected into the grounding system, tower footing system, R. So that's why your tower footing resistance is very important, because the lower the R, the better the energy will be absorbed into the ground. Okay? Any question? Okay, the first one here, we call it alpha 1. This one is alpha 1. Sorry for the... And this one is beta 1 that goes in. So for this case, we already described here. So this one is called beta 1 and alpha 1. So here, the equivalent circuit is like this. We have Z earth and Z equivalent. And this Z equivalent is given by Z tower in parallel with Z earth. And it will give us beta 1 and alpha 1 at this discontinuity. And the surge is actually coming from the left there. And the one that goes into the tower as well as to the left will have the same beta, which is beta 1. Okay? And that continued here, beta 1 Vs, will go down. Okay, so this is Vs. And this voltage will go into the tower and got reflected again at this point, at the bottom of the tower. And you can calculate the voltage that got reflected. The voltage that got reflected is equal to alpha 2 multiplied by V incident. Now, the V incident is equal to beta 1 Vs multiplied alpha 2. Okay? Similarly, the one that goes into the ground tower footing resistance is given by this formula. V transmit, beta 2, V incident. Equal to beta 2, beta 1, Vs. Okay. Any questions so far?